QA, QB, QC, you directly connect these pins to where? So that's the IC chip, input, output, all right? So directly connect A, B, C, D, all these pins to the 7-segment display device. See? This A, B, C, D, E, F, G. See? It's very simple. And you can see that there are 2 stages. This stage performs like a latch. So whenever the data is ready over here, the 8-bit data here is ready, then it's going to trigger the clock, it's not a D flip-flop, it's very similar. It's going to trigger this RS flip-flop and send the data directly to here. So don't, this looks like complicated. It's being inverted, invert again, and then invert again. So don't think about this in that way. Just going to transfer the data directly from here to here, and we'll look at it like why the data from here to here is not inverted or is being inverted. Now it's a serial communication. You see ICR means serial, so the data only has 1 bit, only 1 line. That's the purpose, because you don't want to use 8 parallel bits because it's occupying a lot of pin resource on the Arduino board. You need all the GPIO pins for other purposes. Okay? You don't want to occupy all the pins. That's why we need a serial to parallel converter, which is a shift register. It's serial in, parallel out. So it works like this. So data comes in from here, serial, just 1 line, okay, 1 and zeros. And at some moment, it's going to sample the data and send it here. And then you can see the digital out is being transferred to the input of the next stage of the flip-flop. So it's being shifted down. So the bits are being shifted after it's being transferred to here. It's being shifted down 1 by 1. And whenever all the bits are ready, it triggers all the RS flip-flops here at the same time. So the parallel data will be sent out to the output. As you can see the display on the device. Okay, so you create the pattern here, whatever A, B, C, you turn on some of them and turn off some of them to make the pattern, to make the exact number on the display on the device. So for example, if I want to display a 0, I'm going to turn off this bar in the middle and turn off the data point, the decimal point. Okay, so it's going to show a 0 here. You have to look at the byte, which controls the display over here. That's 8 bits, right? So it's a 1 byte. And what is that byte you want to use for this display? And then send it serially to this 595 chip. And whenever the data is ready, send them out at the same time. So these ones will turn on, turn off corresponding LEDs. A quick question over here. So what if you have multiple digits in the 7-segment display? How can you show different numbers in different digits? So you are thinking about, hey, I have 1 serial in and A parallel out, okay? So this A parallel out is controlling how many digits of the 7-segment display. How many digits? 1. So if I have 2, for example, not going 3, 4, 5, okay, 2. What's the strategy, or what you think? What's the solution to it? Do you need a 2 serial input or just a 1? What is the better solution? So keep in mind, I think this is the very beginning of dealing with digital signal transmission, and it's going to change your whole mindset compared to all the analog world you have learned. This is digital. Why digital is magic? Because it's fast. It's very close. So how do you connect these outputs? So you have 8-bit for the outputs, right? So it's controlling 8 inputs for the display unit. So you have 2. How do you deal with that? Very fundamental digital controlling problem. Okay, you have two. Here's a chip. You got QA to QH. So these are being shorted to here, right? Controlling this guy. So what if you have two? So this is only one input. Remember the serial input is only one line. That's the data line, is only data input to the chip. So do you need two of these serial chips, the shift register chips? No, it's too complicated. So what if you have 10 digits? You are going to insert like 10 chips over there. It's taking a lot of space. It's a very simple application. You just need a one. How to make it work? Yeah, just short them, you know, to all the inputs here, just short them to the inputs here as well. So you are thinking, hey, if I have the same pattern over here, it's going to show the same number. If I'm showing a 0, it's going to show a 0 here as well because all the data lines are being shorted. So how do you display a different number? Yes, and do it really quickly, right? So how to do it? So there's an enable pin. Okay, so let's do it very slowly first. If I display a 5 here, for example, and I display a 6 over here, all right, so I enable this one, and I send the data pattern of 5 serially to here. Yes, it's pumping every single digit for each time. It's like boom, 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 right? Sounds like it's very slow, but actually because you can oscillate really quickly, so it's actually very fast. You can get all the data here to be ready here in several milliseconds. Okay. So send the data pattern of 5 first. Enable this one, disable this one, just turn it off. Don't show anything, just turn it off. So input 5 shows a 5, and then disable it and enable this one and show a 6. And just keep doing that really quickly. So your eyes cannot resolve the changes or the blinking of these two displays. It seems to you guys it's going to be a static 5 and 6 to be displayed on these two devices. Does that make sense? Okay, that's how that works. Okay, so before we wrap this up, I still want to explain how these flops work. It's the same thing as a projector. So you are thinking about how this monitor works. It's assigning every single pixel to the monitor really quickly. Your eye cannot resolve it. There are probably several million pixels on the monitor. It's just assigning every single one really quickly and do the line scanning and then row scanning, column scanning, just scan all the page. As long as it's faster than 30 frames per second, your eye cannot tell the changes, the refreshing of the pages. Okay. And then let's look at the fundamentals of flip-flop. Do it really quick. So what is this device? So what is this called? RS latch. So which is R, which is S? And why is that? R means reset, S means set. So whenever you are setting in the digital system, you are pulling the line to 1. When you are resetting, is pulling the line to 0. Just keep in mind, always. Resetting is 0, setting is 1. So let's see, and just keep in mind, no matter what, it's a RS latch, RS flip-flop, you are always giving an inverted data input to the two lines. You never use 1 1s or 0 0s, unless you want to transfer everything to the memory mode. But however, when you are operating the flip-flop or latch, you need these data lines to be inverted from each other. So if this is 1, this becomes 0, right? So that's the input. The customer can input the signal to it. It's very easy to control. So they are always 0, 1 or 1, 0 like that as the inputs. So if I have 1, 0, what's happening for Q? 0 is going to kill this NAND gate because 0 NAND anything will be 1. Okay, so 1 here, 1, 1, NAND, 0. So if you have S here, Q equals to 1. So whenever I turn on S, I'm setting the output. So that's why this must be S. And if I turn this into the RS flip-flop, it looks slightly different. And I need another NAND gate stage over here. And the middle line is being controlled by the clock. So which is S, which is R this time. Here's Q, here's Q bar. Remember which is S, which is R? RS, right? However, these are not the inputs anymore because these are just some intermediate signal lines in the middle. So these are the inputs. So RS is always like that, but now I have another NAND gate. It only happens when clock is high. It's not an edge trigger, it's a level trigger. So that's why when clock is high, it works. Otherwise, it's being disabled. So clock is always high whenever it's being operated. So which is R, which is S. That's a NAND gate. You got a 1 here, it's an inverter. So that's why here becomes S, here becomes R. Does that make sense? Let's verify it. If I have a 1 here, 0 here. So clock is 1, 1, 1, you got a 0. 1, 0, you got a 1 here. Okay? So see, if you compare to this one, which is S? The bottom line is S. So when here is 1, this becomes 1. So that's why this must be S. Setting, resetting. Okay? And what's the conclusion? What's the takeaway from this example? You only have 2 different signals in digital system, 1 or 0. So the ISR flip-flop, the Q is always doing what? When the clock is high, it's sending what to Q? So here 1, 0, right? You only have 2 options. Here, this is the other option, the other possibility. 0, 1. Because this is reset. Reset is being turned on, so you are getting 0, 1 here, right? Okay? So by looking at Q, whenever clock is high, it is sending what to Q? Where's data? You don't have. It's not a D flip-flop. Sending S. See? 1, 0, 1, 0. Keep in mind, it's critical. So the SR flip-flop is always sending S to Q. It's very simple, actually, right? So whenever the clock is triggered, whenever the clock is active, just send S to Q. That's it. So let's come back to here. See if that is true. So D flip-flop is the data flip-flop, so it's always sending D to Q, no problem, right? But you have the D flip-flop on the top, but all the other ones are SR flip-flops. So keep in mind, SR flip-flop is always sending which to Q? S to Q. Okay, let's see. Let's verify it. But before we do that, let's look at the timing diagram first. Then we can come back to this circuit diagram. This is the clock for the first stage. And this is the data, remember serial data? And this is the clock for the second stage. It's actually like the latch for the final stage, sending the final data out. And this is a clearing line. So whenever this is low, it clears up everything. So no, you don't have to worry about it right now. But let's look at the first rising edge. So the rising edge, this is the first stage of the flip-flop. All right, let's come back. SR clock, right? See, SR clock is triggering the first stage of the flip-flops over here. So SR clock, rising edge, is going to send whatever being sampled over here to QA. So this is 0, but it's nothing. It's unknown. Why? Because clear is still active. It's still clearing up everything. So it's not supposed to be active. So now let's move to the second rising edge. So what's the data at that moment? What's the data being sampled? 1. See, here is 1. So it's sampling this data right now. The sampling of data, and the clear is not active because it's 1 right now, because it has a clear bar, which means it's a 0 active. So it's not active right now. It's high, so all the flip-flops are supposed to work. So it's going to sample 1 here to the first stage of the flip-flops, and then it has to wait until the rising edge of the second stage to send all the data, to send the data out. So that's why, see here, it toggles QA because 1 was sampled over here and waiting until the next R clock, which is the second stage of the flip-flops, which is here, you send it out. It's not ready yet because we need to wait until all the A bits are being sent over to here. And then what's happening? Then start sampling the second data. So what's the data here? Serial. Just one line for the data, right? So it's 0, sample the 0, and wait until the second stage rising edge to send it out. So that's why over here, it toggles the output because the second data being sampled was 0. And you can see the serial data here, all the remaining data are zeros. That's why it's actually shifting the first one, sampled one, to the right, but all the remaining data here are zeros. All the sample data are 0 because of these are zeros. Okay, that's why these are zeros. Now let's come back to the circuit diagram. Now let's see if that is true. I mean, rising edge triggered SR D flip-flop. So serial data, it's a D flip-flop. So for example, this is the data. I labeled this one as D. I labeled it as D. All right, so what is did you see the bubble here? The bubble means not. So actually it's shorting Q naught to this line. So this becomes what? Do you agree with that? So D naught is being sent to here. So that's the SR flip-flop. So sending D to R, which is the inverse of S. Remember, SR flip-flop, we always inverse it. So what does that mean? So the SR flip-flop is always sending S to Q. Okay, so now it's sending what to where? So D naught is shorted to R, and because the RS flip-flop is always sending S, which is R naught, which is D, not, which is D, to here, and this Q naught. So whatever is showing here will be D naught as well. I'll give you a second to think about it. So bubble here, no problem, D naught, okay? And D naught is literally S, okay? The D naught is being shorted to R. It's the SR flip-flop, so the SR flip-flop is always sending S, which is actually R naught, and R naught is D naught naught, which is D, and it's being inverted again, so it's getting D naught over here, okay? All right. So all these intermediate signals will be the inverse of the data, because it's shifting to the next stage. Next stage is always the inverse of the signal. And now you can see that the inverse of the signal is being sent to R, right? Then what's happening for the ISR flip-flop? The ISR flip-flop over here is always sending what to where? S to Q, okay? You can see it's not, so it's actually nothing. It's not inverting. It's inverting once, twice. So it's actually still the data, okay? Still Q, not Q naught. But you can see here, D naught is being shorted to R, so whatever being sent to Q is D or D naught. Here is D naught, right? And D naught is being shorted to R. And remember, it's always sending S to Q, not R to Q. So it's actually sending R naught to Q, which is D naught to Q. So it becomes D. Okay, so whatever the data being sent to here will be sent directly to the Qs. So you need these data to be exactly the data you want to use for the device, not inverted data. So that's the data transfer. Now it's clear, no problem. What about the clock? Is that rising edge or falling edge? See, it's invert and inverted twice. So it's rising edge. What was this one? The second stage clock. Invert. It's also rising edge. That is why you have the rising edge to sample the data. The rising edge samples this one, and waiting for the rising edge for the R clock, and then send to the output. You can see it's being toggled. All right. And now let's come back to the 7-second display over here. There's a critical, there's an argument in one of the functions we use. So the function's name is called shift out. So you can search for shift out Arduino and find out the functions, the arguments inside. But now I want to explain this really quick to you guys. It can be a little bit confusing, and you do need that background to find out the your own version of the code for LSB first. So there are two. So one of the argument is called the shift direction. So there are two options: MSB first, LSB first. And another argument is the data, okay, the 8-bit data. So it's a hex data, for example, 3F, which is 00111111. So here's the data in this function, and that's the shift direction you are going to define in the function as well. So this direction is going to define which bit is being sent out first. So if you use MSB first, this single bit is going to be sent out first. So if you understand the circuit of the 595, you actually can find out that here's the 595. These are all the Qs. QA, QB, QH. And these Qs are being shorted to where? Directly to the LEDs, keep in mind. There's nothing else in the middle, directly. This is A, this is B, C, D, E, F, G, H. I mean, directly, what does that mean? It directly wires them up. You know, so on and so forth, right? Okay. If you are sending MSB first for this data, MSB first, what's going to happen? Remember the shift register inside the chip? If you are sending MSB first from this data, from this hex number, what's going to happen? No, MSB first. So this bit will be sent. So that's the SDR, the data line, right? So this will be sent first, and then so on and so forth. So all the data will be shifted downwards. So you're getting 0. So it's going to be 0, 0 for the bottom 2 bits and 1s for all the other ones. That's MSB first. So are you getting the correct pattern? So what's the display is going to show you? If you have this data here and MSB first here, that's MSB first, right? So what's the data, what's the display is going to show you? So yeah, 0. Because all these are on, but G and H are off. So you can display a 0 over here. Okay. You just do it for all the other numbers. Same concept. You just need a 1 byte for the data if you're using MSB first. However, this is an example for the on the tutorial. And I'm asking you to use LSB first to show the same pattern. So how that works? So what if you do LSB first? How can I display a 0 if I'm doing LSB first? Yeah, so data becomes what? Yeah. Because this will be sent first. So it becomes this. We are using LSB first. So what is this hex number? So in Arduino, when you're coding it up, you need a different data for LSB first, right? So what is that number here? FC. Okay. Got it? Cool. The last thing here I want to talk about is the 4-digit 7-segment display, like what I just talked about. Okay. How to make it work? Is there an activate? How to activate? So here's a circuit diagram of the display. Okay. Like I said, you need to activate every single digit each time, and assign the data pattern and turn it off, and assign the second one, the third one, the fourth one, and then come back and just do it really quickly. So where's the activation pin? Did you see that? So for example, D1. So what is the pin number of the D1? Yeah. So what is 12? It's a common cathode pin of the first digit of the display. So how can I turn it off? What's the way to turn it off? By looking at the circuit. No. There's no way to disconnect it. You have the physical wire already wired up on the board. Yeah, pull it high. So if you pull the cathode high, there's no way that you can make it conductive. Because the highest voltage you can get at the anode is the same voltage level, 5 volts. It's always off, right? So you wanna, if you give voltage high for all, like 1, 2, 3, 4, for all of them, you can turn off all the digits. And then you can start turning 1 each time. You assign this pin a logic low, and then do the serial transmission, get the 595, output that 8-bit to it, and turn it off, and turn this on, assign, turn it off. Don't forget to turn it off. Okay. Otherwise, it's going to show the same data as the second digit, as the next digit, right? Now that makes sense. Understand the trick here, how to make it work. You can see under the camera, it's not really significant actually. You can see these are still blinking, But by, tweaking that delay time for each activation and deactivation, you can make this brightness a little bit different, or the contrast a little bit different as this one. But it just looks very bad under the camera. But in real world, actually, it's a lot better than this. So you're not supposed to 2019 anymore, right? 2022, please. Okay, or show whatever you want to show on the display. Okay, makes sense? So repeat and complete the work in sections 2.1 to 2.4. I think that's it. Everything on the tutorial. So here's the code. See, it's very simple. So assign SSD, so assign the data a pattern, a byte, and then call the update shift register function. You don't have to do all the shifts by yourself. So the function is going to do that for you. So look at this update shift register function. You can see that it pulls the latch pin low, and then do the shifting, okay, and then pull it high. So what's the latch pin? Is the arc clock. So which means whenever it's shifting, you don't want to make any display. You don't want to send the data out, right? You want to disable all the outputs. Okay. So you want to wait. It's a different sequence as the one you see here. That makes sense. I mean, did you get that point? Did you get that point here? So the arc clock is always toggling. However, whatever we are doing here, you don't want this to be toggled that frequently. So it's actually shifting every bit down at the first stage, so that when the data comes in, it's doing like this: boom, 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 boom. And when it's ready, when it reaches the eighth bit, do this together at the same time. Because you don't have control from here to the display. It's always shorted together, just a wire. So if you don't do the control, it's going to display all the intermediate whatever numbers to the display. Right? You're going to control it. You don't want to use that sequence. Right? You don't want to use this. You want to wait until here. However, you don't have to modify or program all the timing diagram by yourself. So literally everything is inside this shift L function. So this function will, I think it's gonna stop everything what is running in the loop. Whenever this is being called, I'm gonna do my job, right? Shift all the bits out and then run the next one. Just like an interrupt, I think it just stop everything, interrupt from the whole main loop, and do the job and come back. Okay. All right, that's everything I want to talk about. Start working on the tasks.